a lot to do and I don't want to keep you too long. But yeah, welcome everyone to the final lesson of our little introductory course. We will finish off with a little bit of material on convolutional neural networks. There'll be time to ask a lot of questions about any confusion that you might have with convolutional neural networks simply because it is such a challenging concept. And then we'll hop into two coding examples, one where we classify everyday images, and then one where we detect malaria in blood cells and classify them as either infected or, I guess, parasitized or, uninfected. But yeah, let's go ahead and see where we left off last time. So last time we left off at our final kind of slide over here where I was talking about the architecture where we have convolutional layers followed by these activation layers which threshold the image. You can kind of see how each of these images is still kind of like a car. It's a little hard to see, but it just shows you how there's these different convolutional filters and each of them isn't identical, if that makes sense. They're all trying to do something different and they're going to modify themselves in order to extract some features that are helpful in making some sort of prediction as to what is contained inside of this image, right? We want to focus on the parts of the car. However, in the initial stages, it might get excited at these curved trees in the background, the landscape, the shadow around the car, and so on and so forth, right? There's so many other things that could distract us from our purpose, but our goal, or the neural network's goal, is to make itself as robust as possible and really pick up on features that help it rather than distract it from its main purpose. We also have these pooling layers, which I said we would skip over. We're going to come back to that in just a couple slides. And then we have our fully connected layers, right? Our final hidden layer is fully connected to some of the neurons in the last layer. And does anyone remember what the word for fully connected was again? What type of layer is that?
Was it dense?
Dense.
Yeah, it was a dense layer. Yeah, perfect. And that's because every neuron in this, or every part of this pooling layer is connected to every single one of these neurons in the final layer because they have to contribute to making those final classifications, right? We need to return some sort of softmax probability for a car, which seems to be like 98%, and then not 98%, it's like 90%, and then like 8% or 10%, 8%, so on and so forth, like decreasing. Also that they add up to 1 or 100%, depending on how you look at it, but simply they have to feed into these features, right, and come up with some sort of probability. And we could see that in our slides. Let me actually flip back to it. It might make, yeah.
So these convolutional neural networks. So earlier when I'd asked, do you individually select outputs or things in a photo that you want to be like monitoring?
Yeah.
I didn't understand your explanation, but I think I get it now. Is it that like from the photo data set you input, is the neural network, is it looking for similarities in each photo?
Yeah, it's looking for similarities.
Create
what?
Like based off of similarities it detects between photos that are given in the data set. Is that how it creates the filters?
Well, it's actually not looking, it's not like comparing images with each other, but it's basically learning off of the X train and the Y train data, right? So it's corresponding this image with its proper classification or its label, and it's basically making the association that these sort of features are located within each of these images. So if I use these features to develop some sort of kernel, I'm going to get excited when I match it to that specific label. So it's like it develops kernels so that it can get excited over similarities for across this, but it's not like directly comparing like one image with another image, if that makes sense.
All right, so it's taking a photo, it creates the kernel,
Mm-hmm.
And so that kernel for that specific label, every other future label, it'll use that same kernel, and then it'll adapt upon that kernel based on every new image.
Yes, exactly. Yeah, and it's
Oh,
not just a single kernel, it's like dozens of kernels, each looking for something different inside of these images and feeding data from one layer to another. And when you have multiple convolutional layers, right, you even get more filters and more kernels every step of the way. And you remember how the image was simply just shrinking the deeper you got into the network, right?
yeah.
So the model is basically if you understand the word abstraction, right, kind of like abstract art, where you don't like understand the meaning usually behind the art, but maybe it just looks kind of like gibberish to you, but maybe to the artist it had some sort of connotation with emotion or symbolism or something like that. That's not the best analogy, but basically as you get smaller, in the layer, you see how these are getting more blurrier. Like some of these layers at the end, they don't look anything like a car to you, right? However, it's representative of like the darker areas where it got more excited, I guess, for certain features, right? So it's not seeing an image anymore at these later layers. At these later layers, it's simply just reading the math behind it, and where there's high values and low values. And yeah, I guess it's developing the kernels and the weights and the biases based off that.
Okay.
And then let me exit out of this. And then maybe this diagram will now make a little bit more sense when looking at a neural network. So we have the input layer, which is this purple. We have all of our hidden layers, which in this case are going to be our convolutional and our pooling layers. And then our last layer is our fully connected or our dense layer, where we get some sort of sigmoid probability, right? Or in this case, it's a softmax probability. Going from 0 to 1, we plot it on the curve. And basically, the highest one is going to be the one that wins, or the one that's chosen as the final label.
Can you explain pooling layers?
Yeah, I have some slides on pooling layers. Let's go. All right, so let's first look at spatial dimensions so that we can understand like some questions that you might have not thought of about convolutional neural networks, and some parameters that we can adjust as deep learning researchers. So remember how I talked about the convolutional operation is simply sliding this kernel across, right? And then once we're done here, this green kernel is just going to move one step down, right? And then it's going to continue across again. It's going to continue across again and again. So if we were to do this, right? So we have a 3x3 kernel and a 7x7 input. So it can be in this first position, right? So count these with me. So we have 1, we have 2, 3, 4, 5. And remember I said that the convolutional operation only returns one number, right? One number. So if we do this 5 across, right? And we can also do it 5 down, right? If we were to do this 5 times across, 5 times across, and we could do that 5 times if we just shifted it down one by one, that's going to take our 7x7 image and simply turn it into a 5x5 output, right? If each of these convolutions is simply returning one number. And that's basically when we have a stride of 1. So what a stride means is how many pixels you shift the kernel by in every iteration of convolution, right? So we're moving 1 over here, 1 over here, 1 over here, 1 over here 5 times. And we would do this process 25 times, right? We would just kind of lower this kernel down by one input and then run it across again and again until we reach the end of the image. However, can anyone see, or I guess let's look at stride 2, right? So stride 2 means we're going to skip 2 pixels at a time. So now we have 1, right? Then we have 2, right? We've jumped 2 places, and then we jump another 2 places, and we have 3. So if we were to do this over and over again, we would get a 3x3 output. So here's where the trade-off comes into play, right? So when we have a stride of 1, it's going to be more computationally expensive, right? Because you have to perform more convolutional operators with every single filter on every single color channel, right? And so on and so forth. However, if we have a stride of 2, we can kind of avoid it being very computationally expensive. It can speed up our training time. However, what's going to happen in the quest to speed up our training time if we use a stride of 2 rather than a stride of 1?
It won't be as accurate. I know accuracy is
It
not like
won't be as
the thing we want to
precise.
use, but
Yeah, accurate, precise are both good answers, and they're a byproduct of that we're losing more information, right? A 3x3 output can simply not store as much information as a 5x5 output, right? So we actually we like to use as small of a stride as possible, but actually stride of 2 does usually work. It's when you try to get larger than that, where you start losing a little bit too much information. And this is something that you kind of just toy around with to see what leads to the highest accuracy. Yet it isn't like the training time isn't absurdly high, right? Taking hours or days or so on and so forth. So this is something that you can look at, but that's the convolutional operation doesn't just happen one step at a time. You could jump pixels and still perform this mathematical operation. All right. So now maybe you might have already thought of this question, maybe not, but what happens if we have a stride of 3? How is this a potential issue for our convolutional operation?
It's kind of skipping over.
Yeah, we're skipping over the pixels, but what's going to happen if we do a stride of 3?
It's going to go off.
Yeah, it's
Yeah,
going to go
square.
off, right?
it doesn't evenly go into it.
Yeah, it doesn't fit, right? So that's very confusing, right? If the model is trying to detect, well, there's nothing to detect, and the convolutional filter, this green little window here that we're sliding across, that's very odd. It doesn't fit, right? It's in for all our intents and purposes, you cannot do something like this. So this is another thing to think about, right? If you accidentally apply the wrong filter with the wrong size when you're doing your own projects, that's going to be strange, right? You have to check yourself on the math here. There's a formula for it. It's not really that hard. It's like the n, which is the dimensions, right, minus the f divided by stride plus 1. If you want to screenshot that for future reference, you can. Otherwise, you can just look it up. It's common knowledge. However, let's not pay too much attention to that. There's a better practice, which is something that I use and most other researchers use, is that I guess what are your thoughts on how we can fit this? How can we fit this if we still wanted to use a stride of 3, but we couldn't change the input image? Is there any ideas that you might have?
Change the kernel dimensions.
Let's say we wanted to keep the kernel dimensions the same. We still wanted to convolve the same thing across the 7x7 output with a 3x3 kernel. It's a challenging question. Definitely something that doesn't come intuitively. But I guess
Can you repeat
let's
yourself?
what?
Can you repeat the question?
Yeah, sure. Let's say I wanted to do this convolutional operation, even though it doesn't fit. Is there something that I could do where I can still apply my 3x3 filter on a 7x7 input? But is there a way I can, I guess, make this fit with the same exact dimensions?
And we can't make the input image bigger.
So yes, we can make the input image bigger. However, you want to keep everything inside of the 7x7 input. Do you have thoughts on how you would make the image bigger?
A border?
Yeah, a border. That's a very, very good answer. And a border, this might be a little bit of an even tougher question, but what would you put in the border?
Empty space. And
Yeah,
that would
that's
be
very, very
white.
good.
Like 1 pixel empty.
Yeah, you would
Yeah.
put 1 empty pixel, or what number
Around,
does
yeah.
that correspond with?
0.
0.
0, right? So 0. And what happens in our convolutional math when we put zeros around the border of an image like this? Remember the
It doesn't.
formula.
It doesn't return it just returns 0.
Yeah, it just
So
returns 0, right? Because remember what we're doing is we're multiplying the weights inside of this kernel times the whatever's inside of the pixel, right? Which would be just 0. So if we were to just surround this image with 0, this is a process called padding. You pad the image with zeros. I think yeah, here we go. If we pad the image with zeros, when you perform that multiplication and addition, right, it just doesn't contribute anything, right? It's just, it's good for us, right? We just kind of ignore it. We just perform this thing called zero padding. And it's very, very common to do so. And oftentimes people just like, they just pad it with zeros anyways. So if their kernel does or does not fit, you're kind of covered, I guess. But that's great. And I'm glad we worked through that. Very, very good. Very impressive. But yeah, you can pad the border with zeros and then it simply doesn't ignore it. Or it simply doesn't factor it into the convolutional math, right? So we're still getting our numbers, yet I guess the border isn't playing a role in it at all. I guess one of the questions that I had is, why can't we, or my first answer when I was asked this question when I was learning this material is I did get the answer. I was like, okay, we can add a border, and then they were like, what should you fill in the border? And my answer was like, you should fill it with the neighboring pixel values, right? You would take like the average of these pixels and fill in the border with that, so it turns into like an extension of the image. And that was just something that I was wondering for the longest time and whether it would work. I've never seen anyone do it, so I guess that's not the right answer. But even when I was watching the Stanford lecture for this, someone asked the same exact question. So just know that I guess it's not common practice to do something like that if you ever have that thought. So yeah, if we have a 3x3 filter and we apply a stride of 1, we simply just drag our convolutional filter across and it will fit evenly, and it just makes everything a whole lot easier, right? When we pad the border with zeros. So definitely an important thing to know, because your math isn't always going to be perfect, right? Imagine trying to calculate the exact like kernel to fit the exact input dimensions, right? That's a pain. Use zero padding, very common, very easy, works very well. All right, so another thing that we can look at is, remember back to how we started with a 32 by 32 by 3 image, right? Or input, and the 3 is the color channels, right? So we perform this convolution, we perform our rectified linear units, or our activation function, right? Our thresholding. And we keep shrinking down in spatial dimensions, right? However, you can imagine, as we were just kind of discussing, right, shrinking too fast is not good, right? Because that means you're losing a lot of valuable information. The more pixels you have, or the more I guess the larger size your input dimension is, you have more information. You're storing more values, and hence you're able to make a far more informed decision about your classification, right? We don't want to boil this down extremely quickly using these convolutional layers, right? Convolutional layers make us lose a lot of information, and it quickly turns to gibberish. So keep this in mind. And we'll come back to it, by the way. I just wanted you to keep it in mind. So here's the brain neuron view of the convolutional layer again. Remember, we looked at this diagram yesterday as well. And I hope now it makes a little bit more sense, where we pass this convolutional filter over. Remember I said that when we pass the filter over that section, it only returns one number, right? And that one number is the dot product, or when we multiply it and add it together, right? It performs convolution, and that's the one number that's going to be fed into the following layer. And take a look at this diagram that they made for these CS231N slides, right? Doesn't that look exactly like the slides that I made for the slideshow that we were covering previously, right? Look at this. We have the axon, we have the dendrite, right? And this is simply the W and X and W and X, and these are all the inputs that are being fed into the model. And inside of this is our f of x, or it's simply this little Greek letter sigma. It means to add together all of the weights times the x plus the bias. So it's W1 x1 plus b plus W2 x2 plus b plus W3 plus x3 plus b, and so on and so forth. That's what it's called sigma notation. You'll learn about it in pre-calculus or whatever. And then the output axon, right, or the y, is simply just a function of all of these weights and biases, right? And that function is going to be kind of dictated by our activation function. So I hope this diagram connects everything together. This is the diagram I learned from in the very beginning. And I thought it is a little bit more confusing than boiling it down and kind of building up our knowledge to connect it together rather than throwing this at you at first. So I hope that this diagram is very readable to you at this stage in the learning. And if you do have any questions, please ask. But I hope that something like this is not looking as confusing as it would be if this would be the first thing that I threw at you. All right, and remember, we're shrinking down in space, right? Remember, we passed that 3x3 kernel over the 7x7 image with a stride of 1, and it just turned into a 5x5 image. Shri asked if I could explain strides again. Yeah, sure. Strides is simply the amount you jump the kernel by in terms of shifting it over. So if we were to have a stride of 1, this is an example of stride of 1, where we just move one block over at a time. You just move one block over at a time. Now a stride of 2 means you just move 2 blocks over at a time. So you're left with a smaller output, right? This is 3x3. But if we had a stride of 1, we're left with a 5x5, right? So you're losing more information at the cost of it being faster, right? It's easier to jump more spaces than it is to jump by one space. Okay, makes sense. Awesome, cool. Yeah, so that's how we get to a smaller image, right? Is because of that stride and because of that convolution, which only returns a single number, right? And these are the activation maps. These are just getting passed from one layer to the next. So let's say we have in our neural network. So when we create a convolutional layer, you know how in the dense layer we specify the number of neurons? In a convolutional layer, we specify the number of filters. Now the filters, you can kind of imagine it like a 3D grid of neurons, right? Just imagine this rectangular prism filled with these circles are inside of this big box over here. So the filters, what that means is that we're going to apply 5 different filters, 5 completely different filters on the same region. So it's like you're taking a bunch of filters stacked on top of each other and you're just trying them all out. So it's 5 completely different filters and they're going to update like by themselves. So it's 5 different neurons looking at the same exact region on the input volume. So you saw how we had that green thing sliding across. Well, you could actually have in this diagram is basically telling us that we have 5 of those green things that are completely different from each other. They don't have anything to do with each other. There are 5 different things performing convolution, yet they're performing it on the same part of the image, if that makes sense. So they're performing it on the same part of the image. And as a result, they could pick up on different features within the image despite acting on the same input volume. So like all of these 5 neurons are all convolving over this little blue section of this red image over here, yet they're all basically independent of each other and they're figuring out their convolutional numbers and their weights and biases independently of each other. And 5 filters is pretty rare. We'll apply like 32 filters or 64 filters in our code. And you can see how the math behind that gets pretty complicated pretty quickly. But luckily, we don't have to deal with that, right? That's the point of having a neural network, is a little bit of abstraction where it does a lot of this math under the hood. All right, so now we're going to talk about pooling layers. So remember, if we were thinking back to here, what was the issue with this image that we talked about? Why is this image bad? Why is this design bad? You can read the text at the top for a hint.
It's shrinking too fast.
Yeah, it's shrinking too fast. And what does that? What does shrinking too fast mean?
Losing more data.
Yeah, we're losing more data. We're losing more information within our image, and we're losing it at a. We do want to shrink it down, but we don't want to shrink it down very fast, right? Because we want to learn in the early layers of the model, right? The whole purpose of the early layers in the neural network is to develop some really good weights and biases to pass on some really useful information to the later layers, right? So in the early layers, especially, we don't want to shrink like this, right? That's absurd. If we lose all our information in the early layers, how are the later layers or the deeper layers going to learn? They're going to learn from a bunch of nonsense or from a bunch of really, really little information, right? So in the early layers, we want to try to keep our information strong. So one thing that we can look at is pooling layers, where pooling layers makes our image smaller. However, it's actually found to be like very strangely good at simply turning the image into a smaller size, yet preserving a lot of the information within it. So what pooling does, you can see how this is a 224 by 224 by 64. And what we simply do is we just boil it down into, well, half its size, right? This is reducing the image's information by a lot. Let's do 224 times 224. That's 5,176, right? 5,176, and let's go into 112 times 112. Dang, we're really like boiling it down by significantly, right? That's a huge change from, let's actually just subtract that. 2024 times 2024 minus, look how many more, like, I guess features or things that we have to perform convolution on is just simply reduced by a pooling layer. And if you look at this image, right, the pooling layer, it's called downsampling, right, by the way, right? When you're going from something larger to something smaller in terms of data, it's called downsampling the image, or you can even downsample data sets and so on and so forth. But you can see how it actually preserved the essence of the image pretty well, right? This downsampled image looks pretty similar to the original image, albeit a little bit blurrier, right? However, when we downsample it, or when we perform this pooling operation, not too bad at all. All right, and let's look at what's happening.
Wait.
So what?
Sorry. So downsampling, can you explain the definition of that again?
Yeah, it's basically going from a larger input volume of data to a smaller input volume of data. Whether that's an image, and in an image's case, right, it's just going from a larger image to a smaller image. Yet what you're trying to do is still preserve all the features of the larger image, but you're just trying to make it smaller, if that makes sense. So you're trying to get rid of as less as possible, yet still downsample it. Let's look up the formal.
Wait.
Exactly.
What?
How does that help? Like in.
Well, basically, if you have very large images, it'll take like hours and hours to train, and basically it's not helping you at all to wait for all this time for training, simply because like a lot of computers don't have the computational power to do so. For like my science fair, all of my images were 3,000 by 3,000, and yeah, I had to downsample them, and it was totally fine. Actually, almost everyone downsamples it, to be honest, simply because you don't need all of the, I guess the neural network is still able to pick up on the essence of the image with the downsampled input, and it makes the operations a lot more easier and computationally efficient, I guess. Even when I was starting out, I was thinking like, okay, I don't really care. Like, I'll just train it for longer. I don't care, and I'll just wait, right? If it's more accurate. But I think when you start actually coding it, you'll see why it's pretty much imperative that you perform something like downsampling.
So is downsampling its own thing, or is downsampling what happens within pooling layers?
Yeah, so pooling layer is the thing that downsamples the image. Pooling layer performs the downsampling. By pooling the image, you have downsampled the image, if that makes sense. And let's let's talk about what pooling is, and then let me know if it's still confusing.
I have
So
one last question.
yeah,
So in the last image, it showed like it went from 256 by 256 pixels, or 224 by 224,
Yeah.
to 112 by 112. Is it each time downsampling occurs to just divide the dimensions by 2?
no, not necessarily. You could downsample it by different sizes if you wanted to. Yeah.
Okay.
Yeah, and we'll talk about the dimensions. So let's say we have a 2x2 kernel, right? Just imagine this as kernels again, because it's used in pooling as well. And we're just passing this 2x2 kernel with a stride of 2, right? So it'd start at the red, and then since the stride of 2 means it shifts over 2 places, so then it goes to the green, and then it goes down 2 places, so yellow and blue, right? So if we had a 2x2 kernel with a stride of 2, there are 4 possible locations that it could be inside of this image. So are you following with that so far? If we had a 2x2 filter or kernel with a stride of 2, there could only be 4 places it could possibly be inside of this little image, right? Yes, no. Oh, there's questions.
Yeah, that makes sense.
Oh, Arush joined. Sorry, I missed your question in Discord. Yeah, just go through the recording, and then you can just DM me on Discord if anything is confusing, and I'd be happy to explain it with you. All right, so we got some thumbs up, and Noah said it makes sense. All right, so max pooling is possibly the easiest thing in the world. You just look at this filter, and you just find the maximum number. Like this is 1156, so the maximum number inside of this is 6, so you just put a 6 in the downsampled image. And this is 2478, so what's the max number here?
8.
8, right? It's just the biggest number. You just put an 8 there. And then over here, you find the max number, right? 3 goes in there, and then in the blue, it's 4 and it goes there. So it's possibly the easiest mathematical operation that we've covered so far in this course. And so why do you think, so we lost a lot of the data, right? We converted these 16 numbers into 4 numbers. However, is there anything interesting that you noticed when we lost all of that data? Is there what did you notice? Or is it just looking a little bit confusing?
What do like the highest numbers mean again?
Yeah, that's actually probably leading to the answer of the question. Is that the highest numbers are representative. It's basically like looking at the entire population and trying to understand a generic trend from it. So like a region such as 1156, right? We have kind of medium level numbers, right? There's about, it's ranging from 1 to 6. So there's a wide variety of things, but we can just boil this down into a 6. Now over here, we have a lot more higher numbers compared to the other regions, right? We have a 2, 4, 7, and 8. And as a result, when we perform max pooling, we extrapolate an 8, and it seems like this region in general will have some sort of stronger feature, some sort of stronger pixel value inside of the image, and hence the spokesperson for this green area is the 8, right? Over here, we have a lot lower numbers. We have 1, 2, 2, 3. So hence the spokesperson for this is a 3. And then we have slightly higher numbers, but more or less the same, so it's a 4. So what we're doing is we're kind of finding like a generic trend of each of these regions, and it's simply given to us by the highest value inside of that area, which is, it sounds a little counterintuitive or a little bit confusing as to why something like this works. However, it works surprisingly well. It's like we're able to get the generic trend of an image simply by performing max pooling. And max pooling is just the most prevalent one. You could also perform min pooling if you really wanted to. And you could also perform something that might make a little bit more sense, which is called global average pooling, where you just find the average of all of these numbers and you downsample it that way. So it'd be 1 + 1 + 5 + 6 divided by 4, right? And then you pass that on to the next layer. However, usually you use max pooling. All right, now shoot with some questions. It is a little bit strange.
So would this be like so when you're taking the highest number from each like quadrant,
Yeah.
would that mean like in the new filter it would be the strongest features from each
Yeah, it would
quadrant?
basically it's like it's not really the strongest features, right? It's like the generic trend. So it feels like in this yellow over here, right? There's a much like maybe there's not as strong. Yeah, sure. I guess you can think of it like strength. There's not as strong of input data inside of this yellow feature as compared to the 8 up here. And maybe this picture on the previous slide will now make it a little bit more clear how we almost grab the entire essence of this black and white looking image when we downsample it. We see almost the same exact shape by performing max pooling, simply because it picks up on the generic trend of the data. Because you can't you can't take a 224 by 224 image and like just drag it like you would inside of like the Photos app on your phone, right? Because that's not how pixels work. You can't like get rid of pixels that way or like squish pixels into a smaller area. And hence you have to downsample it, or you have to use this pooling operation in order to reduce the amount of information that's inside of the following layer or the downsampled output. Any more questions?
What you had said, average pooling, what's that called again?
It's called global average pooling or average pooling. Yeah.
Will we ever use that?
You could try it. It's more like a thing of try it and see what works better.
Okay.
Yeah. It's like, yeah, I don't know how else to put it. It's just one of those things that you have to test out in order to see which one works better for your data set or not.
And so going back to the numbers, so when we go to like a real photo, all these numbers, would they just be colors? Like the color, like 0 to 255 of a color of a pixel?
Yes, and it would be split over 3 channels.
Yeah.
Yeah. And that's only the first layer, right? After the first layer, it's no longer the colors, right? It gets into
Yeah,
some
then it's just the
weights and
pixels.
biases gibberish, right? It's W times the input plus B, right?
Yeah.
So it's a lot
I'm
harder
just
to
curious what
define
like the
what
starting
happens.
value is.
Yeah,
How
the
it's like,
starting values, it's looking at it's looking at the data through pixels. Because that's what an image is, right? It's an array of pixels, and that's all a computer understands. It doesn't know what a car or dog or so on and so forth is, right? All right. If you have more questions, go ahead and ask in the chat, and I'll come back to it. But otherwise, I will move on. Actually, I think the last thing in this slide was fully connected layers. I think we understand them by now, right? It's simply yeah, I think we're good on that. All right. So a summary of this. Don't ignore some of these bullet points. I just didn't know how to delete them since I just kind of grabbed this PowerPoint from online. But convolutional neural networks are simply a stack of convolutional layers, pooling layers, which is called a convolutional stack. You pair a convolutional layer with a pooling layer, and we'll see that in the code. And that's called a convolutional stack, or at least I call it that. Actually, I'm not really sure if that's the proper term for it. And then at the end, you have some fully connected layers to kind of result in your final classification, right? Because why can't we just have fully connected layers everywhere when we're dealing with image data?
it wouldn't be as accurate because it would only be passing through like one set of it'll be passing through less set of equations and refining stages.
That's a good thought. Yes, the algorithm itself for convolutional is more effective at analyzing image data, but also it's pretty unrealistic, right? Imagine taking all these thousands and thousands of pixels in the input neurons and then trying to adjust thousands and thousands of weights and biases over and over and over and over again. We do want to shrink it. That is one of our goals, is to make it easier and faster for the model to detect these things. So we use the convolutional and pooling layers in order to do so, to pass it from layer to layer. Remember, it's spitting out like these feature maps. Where were we with the headlight example, right? this is what's going from one layer to the next layer. We want to develop these kernels, and then at the very end is where it's kind of more appropriate to use to use something like a dense or a fully, aka a fully connected layer, right? So yeah, I think that was it. Oh yeah.
Wait, I'm actually confused now with what you just said. Like, could you just explain?
Yeah, so convolutional layer, your answer was right, but also you do want to have a dense layer at the end of it in order to kind of aggregate our predictions into the proper classifications. And it's just like dense layers can't really be used like the convolutional operation, right? Dense layers would simply be performing these weights and biases, but it's not performing things that work especially well on image data. So that's why the artificial neural network that we created for the MNIST dataset last time, it's not the best way to do it. Usually you would try to use a convolutional neural network in order to perform the MNIST classification, which I encourage you to try on your own, by the way, outside of the class. And there's dozens of tutorials for using a CNN on MNIST data if you ever get stuck.
But so why would you? So in convolutional neural networks, with each layer, would that? So previously we were having them all as dense layers, each neuron connected to every other neuron.
Mm-hmm.
Convolutional neural networks, would we not want that?
Well, basically, you're shrinking them down, right? A convolutional neural network simply looks different than a dense layer. If you remember way at the beginning, this is what a convolutional neural network. Oops. This is what a convolutional neural network looks like. It's like squares of these feature maps that basically get smaller and smaller as we go down. However, they could get like thicker, right? But they get smaller and smaller in length by width until the very end where we want to perform this one-dimensional dense layers, right? These fully connected layers, that's what this F6 layer over here says. And we want to basically take this square data and we want to flatten it, just like numpy dot flatten, right? That we learned in the research class. And then that's going to feed into our output layer over here. So this is really preserving these feature maps from layer to layer through convolutions and through subsampling. Subsampling simply means like downsampling, which simply means pooling, right? It's just a pooling layer going from one space to the next. So yes, to your question.
Okay.
Yeah, the architecture is just different than an artificial neural network. All right, but the last thing is that I wanted to note is sometimes you can overfit, right? Even in convolutional neural networks, it is very easy to make your model overly complex, and as a result, the model will start to overfit. This is a very nice example of what's overfitting. You can see that these X's over here, right? So this is what's called dropout, and dropout is a way to reduce overfitting because what it does is that it randomly turns off some of the neurons in these layers, right? You see this is an example of some dense layers, right? Originally, they were connected to every layer of the following output. However, dropout randomly turned off some of these neurons, and as a result, the model won't start memorizing like some of these features, if that makes sense. Like, we can take a look at this example over here. Let's say we were making a dog and cat classifier, right? So if we're making a dog versus cat classifier, would a neuron that detects if they have an ear, would that be useful to us?
No.
No, right? Because dogs and cats have ears, right? So that's like a redundant neuron. This neuron has picked up on something that's pretty stupid, and it's just going to memorize like the shape of a dog ear and the shape of a cat ear and just kind of feed it into the model. That's not good because that's not going to apply very well on real world data, on data it's never seen before. So dropout, by the way, it drops like a random number of these. However, like it is very effective at reducing overfitting. So if you see overfitting in your model, it's very good to add in a little bit of a dropout layer.
The dropout layer, so it randomly selects neurons to drop out?
Yeah, it randomly turns off. It shuts off neurons randomly. And it picks random neurons, but you specify like the percentage to pick. So like dropout 0.5 would randomly turn off 50% of the neurons. It's a pretty common number. 40-50%.
But what if it turns off like useful neurons and keeps the bad ones?
Yeah,
Does
so
it-
that's the, I guess, the part of training, right? So it's going to happen many times, and as a result, the essence of the important neurons will still be there, because those are going to have more of a say in the final classifications than the ones that picked up on wrong things, right? Remember, training is an iterative process, so it'll drop out 50% random neurons the first time, but the next time that it goes through the data, it'll drop out a different set of 50% neurons.
Oh, so it'll drop. Okay, so it drops out a different set each time it iterates, and whichever
Yeah,
one
like through the
performed better,
epochs, right? And every single time.
and does it just so whichever one performs better, it keeps that, and then keeps on dropping out off of that?
No, it won't. It won't like it won't say that, oh, this one performed better, so I'm gonna keep it. It'll still keep dropping out random ones. However, the at the very end, right? At the very end, you're left with a trained model, and with a trained model, those neurons that are returning higher values are gonna have more of a say in the final classification than the neurons that were pretty useless. And when they dropped out, it didn't affect anything or very much of anything at all.
So does the dropout function like interact with the training of the function, so it knows which neurons like are more heavily weighted? Like
No, it randomly turns them off during training. But however, like, so let's say I drop out 50% neurons, and in a hypothetical situation, let's say all of those neurons were useless and the model was still highly accurate without those neurons. So as a result, the remaining 50% of neurons will have a bigger say once the model is completely trained in the final output, and those neurons that were turned off and didn't have much of a say at all, they're not gonna, when we apply it to the testing data, they're probably not going to play as big of a role in doing so.
I'm just confused. How does it not drop useful neurons that are carrying useful information that can really help identify distinct?
Yeah, no. It does drop useful neurons sometimes. It just randomly drops a percentage of the neurons, and as it's like I'm looking it up here, and it says the ones that, so when you turn them off, if you were to turn off a set number of neurons and it negatively impacted the performance a lot, the model would be able to understand that the neurons that you turned off should be more responsible for the final classification. That's the word they use. They use responsibility. So as a result, in the fully trained model, when we're applying it to testing data, the models the neurons that were deemed more essential, which is determined by if they were dropped out by, it's not by accident, but if they were dropped out and that really made a negative impact on the model, then they would have more of a responsibility on figuring out what's inside of the training data, if that makes sense.
Wait, so you're saying that even if they are dropped out, if it had a negative impact on the model, they would then say that these ones that were dropped out should have more of a say?
Yeah, they're not dropped out like permanently, if that makes sense. Like they're just dropped out for that training iteration. It's like the neural network is turning off 50% the first time, and then it's turning off a brand new set of 50% the next time, and so on and so forth. It randomly like picks neurons to drop out so that it doesn't overfit. Again, that's like overfitting is like having the answer key to the test, right? So this is basically like, I guess, yeah, it's like randomly making you forget some of the answers from the, if you have the answer key in your hands, I guess. Let me see if
I get it now.
Okay, let me see if there's a little bit of a better explanation online. Yeah, it says dropout forces a neural network to learn more robust features that are useful in conjunction with random subsets of other neurons. So I guess, well, if you look at this diagram over here, right? So the CAT score is determined by like has a tail and has claws, and that's gonna, those two working together, right? With all the other neurons dropped out, is going to basically contribute as like a pair, right? So those random subsets that are still remaining are going to be seen as like a group contributor to determining the final output, since the other neurons are dropped out. And as a result, if they positively impact performance, then we know that they're going to take a higher responsibility. And if they negatively impact performance, or if they don't impact performance much at all, then they're going to have a lower responsibility in determining the final classification of whatever our image is. All right, that is dropout, and I think that is actually it. Okay, not too bad on time. I think we can finish by 12:30. All right, go ahead and create a new Colab notebook, and once you've done so, if you have questions, let me know about all the slides that we just covered. Wait, do I have more slides? No, we're good.
Can you just like overview the first slide that it was like showing the process?
Yeah,
like
sure.
it showed like the handwritten A and then all of the
Yeah. Let's just look at Google Images for CNN architecture so that you can see the similarities between a lot of them. So each one is obviously not going to be the same. Those slides just picked some random example from the internet, right? Here's an MNIST. This might be a little bit more applicable to the example we already went over. There we go. This is a good image. Can I zoom in? There we go. All right, so this is a little bit more understandable, I think, than even that image over there. So we have an input image, right? This is an image of a 0, right, from our MNIST data set. It's 28 by 28, right? It's 28 by 28, so there's 784 pixels inside of this. What we're going to do is we're going to perform convolution. We're going to perform convolution with some sort of kernel. And as a result, this second layer is going to be smaller, right? Because whenever we convolve, we only return one number from it. Let's say we were doing a 3 by 3 or something like that, some sort of convolutional kernel. And then we're going to threshold it with our rectified linear unit, right? We're going to, you saw that in that Tesla example or the car example. However, what we want to do is we want to learn from this, but we also want to kind of reduce it in size. So what we're going to do next is we're going to downsample this. We're going to downsample this, whatever is spit out by our convolutional layer. And we're going to downsample it by simply pooling it. So remember, pooling still preserves the general information that was inside of this convolutional layer. It still preserves it. However, it's at a much smaller input, or it's at a much smaller, I guess, dimensions, layer dimensions, spatial dimensions, than it was in the previous step. Now with this, let's say we're almost done, and when we're almost done, we like to slap on 2 fully connected layers. One fully connected layer is going to be like you'll see in the code, it's going to be a lot deeper. And then the final fully connected layer is only going to be 10 neurons long, right? The final fully connected layer has to match the number of classifications in our final output. And that would be 0 through 9 or 10. However, this is a very, very simple convolutional neural network. Usually we have like a bunch of these convolutional layers followed by pooling layers before we get to the fully connected layers. And we can probably see that in something like this. Or here's an even better image. Where's the picture? There we go. There we go. So here we have a classic convolutional neural network. I think this is actually the same exact example. They just didn't draw in the A. And here we have the input. We've convolved it. This convolution, it actually looks the same as the input. So what do you think the kernel size was on this convolution? Or no, it looks slightly smaller. But you can actually perform 1-by-1 convolution and go from the same dimensions to the following layer. But ignore that. I don't use 1-by-1 convolution. But yeah, and then you pool it, and then you convolution it, and then you pool it, and then you could convolution it again and pool it again, and so on and so forth. You could keep doing convolutional and pooling layers, and that's what means like a deep neural network, right? More than 2 hidden layers, and it gets deeper and deeper with the more layers that you have. And at the end, we just have 2 fully connected layers that spit out our final output.
Wait, so each time one convolutional layer has been performed,
Mm-hmm.
is it common for it to be immediately pooled afterwards?
Yeah, because it makes it easier for the following convolutional layer to perform another operation, because the data is downsampled, right? So hence, we don't like it's just computationally more efficient to do so later. However, we don't want to shrink too fast, right? We want to keep the early layers to be like, we don't want to start out by pooling the image simply because this first convolutional layer will pick up on a lot of the useful features inside of the data. But yes, you're
Wait,
right.
I'm confused about, you just said you don't want, like, the way they did it here, you would not recommend doing, but pooling so close to the start?
No. Don't pool right at the start. Like, don't have pooling as your first layer.
Oh, yeah, that I understand.
Yeah.
That you lose a lot of data before you really collect any.
Yeah, but it is very common to always follow a convolutional layer with a pooling layer.
So
Yeah.
basically, does it like keep making the images smaller until like, is that basically what convolution is, like with the layers?
Yeah, it's not.
pooling?
It is making the image smaller, but that's simply because it's able to represent that region of an image with some sort of number that's like representative of the whole data set. Like, let's say, it's not the best example, but like a GT class, right? Let's say you have like like those gifted and talented classes that they have in elementary school versus maybe a regular class. They're taking the same standardized test, but maybe the gifted and talented class scores like a higher like result on that test, and hence the average of all of those scores is pretty representative of all the kids in the class, and that's the generic trend versus something that might be I guess slightly lower in comparison, which is representative of the average scores of the other class. So you're able to pick up on the trend that the GT class on average performs better on testing simply based off 2 numbers, if that makes sense. You only need 2 numbers and you can pick up on a trend. Does that make more sense as to why when it gets smaller, it still has useful information in it, which is just the trend, but it's just
Yeah.
like one number is representing many numbers.
Yeah.
All right, cool. Good questions all around. And by the way, like this sort of material that I'm teaching you right now, when I first learned it, I did these like online courses and watched these lectures online like 2 to 3 times before like I actually was able to explain it back to other people, if that makes sense. It's like if I asked you to present these slides back to me, even if you understood them, it's pretty challenging. So I feel like repetition is really key to some complex materials such as this. Repetition and just basically paying attention to the material and like reading some notes on how you understood it the first time and maybe how your perspective on understanding it the second time. Drawing analogies, which I'm trying to do right with the test scores or so on and so forth. That also helps a lot. But yeah, let's hop into some code. Let's make some convolutional neural networks. So I'm going to do the, let's see what I have. Create a blank notebook if you haven't already. Let's do the CFAR10 dataset first because it's simpler. Where's my code for that? All right, I have the CFAR10 dataset. Let's see. Okay, the training was fast. All right, sick. Okay, so what we're going to do is explore the CFAR10 dataset. So I'm just going to give you a brief overview of what the CFAR10 dataset is. You don't have to write this down, by the way. So it stands for the Canadian Institute for Advanced Research. It's a very, very common color data set. And it has 60,000 color images, which are 32 by 32 in 10 different classes, right? So you should already have an idea that our final dense layer is going to be 10 neurons. and there's 6,000 images of each class, right? So if there's an even number of images in each class, right, that means we have a balanced data set, right? Because each classification has an even number of data, even spread of data. And the 10 classes are pretty random, but yeah, it's a very good demonstration. There's airplanes, cars, birds, cats, deer, dogs, frogs, ships, and trucks. So pretty like weird assortment of, I don't know, like automobiles and animals, I guess. But yeah, it's a very, very good demonstration, and that's showing us how a convolutional neural network is pretty good at image classification with a setup like this. So I'll call this deep learning CFAR. And the nice part about this is that the data set is already stored inside of Keras, and we don't need to download it. Downloading image data sets is a struggle within itself, simply because it's so large. They can get up to hundreds of gigabytes, depending on how large your images are. All right, so import CFAR 10. I think there's like CFAR 100 as well, where there's 100 classes of things instead of just 10 classes of things, if you ever want to play around with that yourself. And what we can do is create X-train and Y-train. You should use a capital letter, but in my answer key I have lowercase and I don't want to make typos, so I'll just copy it exactly. So we have X-train and Y-train, X-test and Y-test. This looks exactly like our MNIST commands, if you remember the code from yesterday. And we're going to do cfar10.load data. And the load data function is really nice with these inbuilt functions because it already organizes it into X-train and Y-train for us. Yeah, it's very convenient, I guess. Let's go ahead and run this. It'll take a second. It's going to pull the data from the website, whatever, Toronto University of Toronto, or wherever it's stored. And then let's take a look at some of the, I guess, the data. Yeah.
I got an error. It says X-train is not defined. I do not know why. I put the equal sign for the load.
Did you follow the
data.
commas and everything exactly?
Yes. I'll just run it again. Oh, it
Alright.
works now.
Wait, really? Just running it again worked?
Apparently.
That's very strange. Okay. But yeah, let's take a look at what our data is looking like. Let's go ahead and print out like 5 of these Y-train. And you see that we have 6, 9, 9, 4, 1. What is this? What is this data over here? Any ideas?
Pixels, pixel values.
Not pixels. Remember, that's going to be stored in our X data.
Oh, is it the corresponding label? Like there's an array of each labels: cars, dogs, trains, horses.
Yeah, exactly. Yeah, and they're just matched to like one of these numbers. Awesome. Yeah, I can actually just, if you look up like CFAR classes online, it'll come up. So I don't really like, there's no need to memorize like what these are corresponded with for the sake of the activity. But yeah, if you want to look back at them, you could look up what the sixth label is, I guess, or we could just take a look right here, right? I don't know if this is in order. That's why I wasn't showing this, but this is airplanes are zeros, 1s are cars, 2s are birds, 3s are cats, and so on and so forth. But yeah, nice. So these are our labels, right? This is the true values of what is inside of it. Now we're going to have the pixels. Let's just go ahead and print out the first one. Here we have it, and this is just simply a 32 by 32 array of pixels. Yeah, and that's all there really is to it. You can press the X, by the way, to get rid of that really long print statement, and then you can just run it again later if you really wanted to. let's see what else we can have here. All right, so do you remember what we needed to do when we were standardizing the images? What did that mean?
Wait, I'm sorry. What did you say with the X to get rid of that? What?
Oh, like when you printed out X train of 0, you see how there was a really long list of pixels?
Yeah.
Yeah, you could just, there's like an X button. Like if I were to run this over here, and it's kind of annoying to like scroll past this every single time, right? So you can like clear the output by pressing this X over here.
Oh.
Yeah, it's just like getting rid of having to scroll past that every single time, which I find annoying sometimes. But yeah, that's completely irrelevant. It doesn't have anything to do with the code. But yeah, back to my question. What does it mean to standardize the images? How did we standardize those MNIST images?
We flattened them.
We flatten them later at the end. There's something else. How can we feed in these pixel values directly into the convolutional neural network? If I were to
No.
run this, can we feed 177, 144, 116? Can we feed these numbers into the model?
Did we do like? I'm looking back at our previous lesson. Was it the step where we did like like the two categorical?
That's going to be another step. Yeah, that's for the Y data, but this is for the X data. But yes, that is one of the steps we will be doing. Can the model read on a range from 0 to 255? How can we standardize these values?
Oh, we have to reshape
Reshape?
and
What do you mean by reshape?
oh, we have to do the thing where we divided the values by 255.
Yeah, right, because our model is only going to read these on a range from 0 to 1, if you remember that. So yeah, awesome. Yeah, we're gonna just turn these into values from 0 to 1. And actually, since we did this step yesterday, we can actually we can make this actually a little bit even simpler. If we did it in 2 lines of code last time, now we can just do it in 1 line of code as such. And go ahead and do this for X test as well. And it should look something like this, and you run this. Now we have standardized images. Now we can do what Shreyas was saying. We're going to one-hot encode those labels, right? We don't want them to be like, what was it, like 69941 or so on and so forth, right? We want one-hot encoded labels. So we're going to do that. Do that for your training and your testing data sets. And for the sake of demonstration, let's go ahead and print out the first 5 of Y-train to see if we did it right. Oops, that should be Y-train. Make sure to not edit this in the same cell, otherwise it'll perform it again. Y-train 5. Wait, I'm not sure if it did it correctly. Oh. If you see something like mine, you're going to have to run it again from the beginning. I basically did 2 categorical twice, if that makes sense. All right, much better. This cell should look something like this. 1, 2, 3, 4, 5, or 0, 1, 2, 3, 4, 5, 6. And then we have 9, 9, and then we have 4, and then we have 1.
Wait, what does the 2 categorical do again? Is that one-hot encoding?
Yeah, it's one-hot encoding. And we can see that over here, right? When we print out Y-train, this looks like one-hot encoded data, right? And the 1 is put at the location 6, right, the index. And then the 1 is put at the index 9, 9, 4, 1, which matches up with when we printed out the first 5 things up here, right? 69941. And that should match up with these 1 hot encoded labels over here. All right, and I hope you have that so far. Let me know if you don't, but we are going to start constructing our model. So remember, our type of model is a sequential model. And then from keras.layers, we're going to import a bunch of layers. So now, knowing what you know about convolutional neural networks, what are some of the layers that we're going to need?
Dense.
Dense.
Yeah,
Pool.
Cool.
pooling. Yeah, and that's, we're going to, more specifically, we're going to use
Max
max.
pool.
And remember, we're working with 2D data. There is maxpool 1D and maxpool 3D, but usually you just use 2D. What else?
This is a little unrelated. Exactly what is sequential again?
Sequential just means it's a model where we can add one layer after the other.
Okay.
It's just like the structure of model, right? We add a sequence of layers because the model is we're going to add one layer and then another layer and so on and so forth, and it just adds them in a row. It's just like the type of model. What are the other layers in a convolutional neural network? There's quite a few. We still have a bunch missing.
Hidden layers.
Hidden layers just refers to anything in the middle. So it's like a generic category, right? It's just like input layer, right? Input layer isn't a type of layer. It's just like what the first layer is, right? Same with output, right? Output isn't a type of layer. It's just the name for that final dense layer.
Like kernels, that's part of the layer.
Kernels will be inside of the layer. Kernels will be inside of the layer. Yeah, convolutional layers, right? So and it's called conv2D. Perfect. How many more do we have? We have 3 down. We still have 3 to go. 3 to go. One hint is we have a type of layer that reduces overfitting.
Isn't dropout a layer?
Yep,
Dropout.
dropout is going to reduce overfitting. What else? What's the thresholding layer called?
ReLU.
Yeah, which is the activation layer, right? Activation. And we're going to pass in ReLU inside of this activation layer. And then there's one more. I guess it's kind of never mind. It's just the flatten layer because we have to flatten this 2D data into 1D data at the very end in order to feed it into our dense layer, right? Because the dense layer doesn't take in 2-dimensional data, right? That doesn't make too much sense. So we have to flatten our 2D like convolutional and neural or convolutional and pooling layers into 1-dimensional in order to pass it into a dense layer because a dense layer is 1-dimensional, right? All right, great. We worked through that. So now we have all of our import statements. Run that, and let's start constructing our model. What's the first step in constructing the model?
Model is equal to sequential.
Yeah, we have to specify the type of model, right? And like for our intents and purposes, it's pretty much always sequential. I don't actually know the other model types. And then what we're going to do is just add a bunch of layers. This is going to we'll construct one stack together, and then we can just copy paste it over and over again. So we do model.add, right? Let's actually add a little enter beyond the sequential so we can see what we're working with. All right, so our first layer, what is the first layer that we want to have over here? If looking back at the architectures with the letter A and the so on and so forth, what is the first layer? In the Tesla example.
The convolution layer.
Yeah, the convolutional layer. So we're going to do conv2D. And what we specify next inside of this is we open another set of parentheses up, and we're going to specify first the number of filters, right? The number of filters inside of this. Remember, the filters was like the number of neurons that were stacking on top of it. And we like to use powers of 2. 32 and 64 are usually very good numbers to work with. And then what did I say about kernel sizes? What are kernel sizes usually? They have 2 characteristics to them. How do we usually pick a kernel size, or what numbers do we usually work with?
Odd numbers.
Yeah,
smaller
odd numbers is one of them. And not only are they odd, but they're usually
Prime.
prime. I guess so, yes. They're like 3 and 5 are both prime, but they're small, and they're usually very low numbers. So we can use 3 by 3. That's a pretty good kernel size. So what we're gonna do is we're gonna add our padding, and we're gonna call it padding equals same. I think this is the thing that 0 pads our border. I need to check on that actually, but I'm pretty sure that's what it does. Let me check what padding equals same does really quick. Padding equals same.
Wait, so that first part, convolution 2D, and then that 32 and 3 by 3. What is that exactly? Is that the number of kernels and the dimensions of the kernels?
So this is the number. Yeah. So this is the number of filters. Yes, this is the number of kernels, and this is the size of the kernel. Yes. And yeah, we can probably look at the keyword arguments to, yeah, so you do filter, you could do filters equals 32 and kernel size equals 3 by 3. That might make it a little bit easier for you to see, such as filter equals 32 and kernel size equals 3 by 3 as so, right? I just usually don't write them down, I guess because I'm just used to it. Yeah, padding equals same as does that. The only other option is padding equals valid, which means no padding, which is not something we want. All right. And then what was the last thing we need to pass in is the input shape of this, right? So what we need to do is just call x underscore train dot shape. And then remember xtrain dot shape. Xtrain is it's like an array of images. So we need to go past that outer set of brackets by doing 1 colon. Yeah, just some basic array slicing. All right, so after the convolutional layers, now we need to add our activation functions. So we're going to do model.add activation. And the type of activation we use in these layers is the ReLU activation, rectified linear unit activation. And yeah, I guess that's pretty much it for that. What we can do is actually just take this little stack over here, and we can just paste it again right here. And this time, let's go ahead and delete filters equals and kernel size equals. And we can actually also delete padding and input shape. So actually we didn't really need to copy that. You should just be left with something like this. Because it's gonna actually infer the input shape from the previous layer, so that's why we don't want to specify it. It'll automatically pick up on the input shape because remember it gets smaller. So it just picks up on the input shape from the previous layer. And then we're going to have an activation layer again. I was wondering where Noah went. Looks like his internet went out. Give me a second to. All right, let's move forward. We still have a lot more layers to do. We're going to create a pretty nice, yeah.
So this model.add activation, is that, so now starting from here, those are our layers?
Yeah, these are all of our layers. Every single time we do model.add, it's another layer.
So then so that first one was just importing our image, right? And just like setting the parameters for the function?
Yeah, and we're gonna feed that into this model that we're constructing, basically. Yeah, exactly. And then after this, since we have you can kind of imagine the convolutional layer and the activation layer as like almost like they're two layers, but they're working pretty much together. So now we can add our max pooling layer to start downsampling. And there is no one size fits all, by the way. These are things that you have to really play around with. This is just something that I found to be reasonably effective on the CFAR data set without overfitting. And now I did notice that it was overfitting, so I periodically added some dropout. So over here, I'm going to add model, add dropout, and I'm going to drop out 25% of these neurons at this point. All right, and now we have a decent convolutional stack. So this is going to perform all the way from convolution to activation to convolution again to activation again to pooling and then randomly shutting off some of the neurons. But I don't want to stop here. I want to create a deep neural network. And by doing so, I can actually just simply like copy all of this again. And this time I'm going to paste it. However, as we get deeper into the neural network, remember, we get smaller in size, we get smaller in image size. However, we can add some more filters to make it a little bit more complex. So if you remember the image that I had, it was, or the architecture image, where was it? Let's see. Stanford CNN slides. Let me pull that up. So if you remember this very first diagram over here, you see how the image is getting smaller, but there's like more feature maps, right? There's more of them, if that makes sense. So we can add some more filters as we get deeper over here. So let's go ahead and do filters equals 64. And then again, we're gonna infer the previous stuff so we can delete all of this. We don't need any of this. We'll just do filters equals 64 and keep our 3x3 kernel size. And let's go ahead. Actually, wait, no, we do need the padding here. I've misspoken. And the rest of it, I think it will be the same. Actually, let's go ahead and make this deeper. It wasn't in my example, but let's make this 64 as well. I think it'll perform a little bit better. But yeah, here we have another stack. All right, now we're done with the convolution and the pooling part of this. And I'll paste this in the chat so that in case you made a typo, you can just copy paste mine in. But now what we're going to do is feed it into the dense layers. We're going to feed it into the dense layers. So in order to feed it into the dense layers, what do we need to do first?
We need to flatten it or like make it one-dimensional.
Yeah, exactly. We're going to make it one-dimensional. 1 second, guys. Let me send Noah a message. All right. So let's go ahead and add a flatten layer. Model.flatten. Wait, no, this should be model.add as such. And there's nothing that needs to go into it. It's simply going to flatten our output from the previous layer. It's just going to flatten it into 1 dimensions. And now what we like to do is we like to have one dense layer that is kind of like, it has a higher number of neurons, either 512 or 1028, something like this, before we actually go into, this is something I'm not going to explain because I'm not very good at explaining it, to be honest. But if you look up as to why we have a final dense layer, you might find a good explanation online. But we like to have two dense layers with either 1028 or 512 neurons. We have one more activation. And now at the very end, by the way, this is something that does make sense, is that we want to have a high number of dropout over here. This is our last chance to reduce overfitting before making our final classification. So we actually drop out 50% of the neurons, right? That's a huge number. We're dropping out half of our neurons because we don't want our model to simply just memorize the images, right? We want our model to learn, not memorize. And that's really what it's doing over here. All right. And then what is our final layer? What is our final dense layer going to have inside of it?
10.
Yeah, 10, because we're going to have 10 different types of images. 10 over here. And then we need one last activation. And what type of activation is it this time?
Sigmoid.
Not sigmoid. This is not binary.
Oh, wait.
Called
Oh.
max.
It's softmax.
Yeah,
softmax.
softmax. Perfect. Which is just sigmoid, but from multiple classes, right? All right, and then last but not least, we need to compile our model, model.compile. And the optimizer we like to use is the Atom optimizer. What type of loss are we going to be using for classification? Take a peek at the last lesson code if you don't remember.
Mean squared error.
That's for regression.
Oh, is it the,
Categorical
the
cross entropy.
categorical- Yeah.
Yeah. Categorical cross entropy is our loss function. Categorical, and if it was a binary, we would use binary cross entropy. Categorical cross entropy, and let's say we want to keep a tab on accuracy. So let's do metrics equals, and then it's a list of metrics that you could monitor, but we just want to monitor accuracy, so we'll just type that in. Yeah, make sure your spellings on these are correct because these are actual like they have to be spelled correctly. It's not just your name for them. They have to be spelled perfectly. All right, we did a lot there. If you accidentally missed something, what?
That model.add dense 10
Yeah,
is that the output layer?
yeah, that's the output layer, correct.
And then that model.add dense 512. So what exactly is this layer for?
I think it's just like good practice to have some sort of fully connected layer before feeding into the final fully connected layer. So what you do is you flatten all your data, then you feed it into a large fully connected layer, and then you take that large fully connected layer and you fully connect it to the final fully connected layer.
So wait, I'm just a little bit confused though with how what exactly does the convolutional layer do and what exactly does the activation layer do? I'm a little
Yeah.
I get the purpose of them, but what exactly do they do with the data? I know what all is happening, but what specifically is their role?
Well, they're simply hunting for patterns, which is what you were asking about last time. They're simply hunting for patterns in the data. One such pattern could be something like a vertical line or a curve or so on and so forth, right? Different shapes in the data. It could be edges, shapes, contours, so on and so forth. It's simply hunting for patterns in the data, and that's what it's doing. The activation layer is just a thresholding feature. Where is it? The activation layer simply turns this image into like these black and white representations of the previous layer.
So so wait, I'm confused. What's the point of them then?
Well, you have to basically have an activation layer because that's what needs to be fed into the following convolutional layers, if that makes sense.
So they just changed the color scale of the image?
Yeah, they're basic. It's called thresholding. I guess I would look up what thresholding is and like a video all about thresholding in order for it to make sense. I guess for the sake of time, because I do want to get to both of the examples, I'll keep explaining about convolutional layers because I think that's harder to understand. Thresholding layers will make a lot of sense if you just watch some video that's dedicated on them. They're not very hard to understand. It's basically, yeah, what is the formal definition for thresholding? I guess because I understand what they do, it's hard for me to explain it because I just know what the word thresholding means. Thresholding is used to create binary images, which means black and white images of whatever is in the previous layer.
So they just create black and white images?
Yeah.
And then wait, does the next convolutional layer, does it convert it back to color, or does it just perform its functions on the black and white layer?
It just performs the functions on the black and white, and that's why it turns it into a grayscale image again. You see that over here, right?
Mhm.
So then we need to threshold it again. Like you have to threshold it every time because otherwise it'll just keep, every time you perform convolution, it turns it back into a grayscale image, so then you need to threshold it again and again. Does that make sense?
Yeah, now I'm getting it.
Yeah.
One
And
last
actually,
one.
oftentimes, I think you can actually pass the activation function into the convolutional layer itself. Yeah, you can actually literally write activation equals relu inside of this, and then you can actually just delete this. They're actually they like work together, if that makes sense. You could literally put it inside of this if you wanted to. But I just wanted to have them separate because I think it's a little bit neater. I like to have it separate at least.
And one last one. So
Mhm.
so the way you have it is there's the first initial convolutional layer,
Yeah,
and then there's an activation, convolution, activation, and then there's the pool.
yeah.
Is it like this 2 convolution and 2 activation layers and then you pool? Is it typically that's the syntax for it? You only do 2 convolutional and 2 activation, or could you do like 3
Yeah, that's a really great question, and there's simply like no answer to that. Like you have to like try them and see what is making sense, I guess.
So it can
And
vary.
I remember people telling, like, I remember asking this question as well, and people would tell me the same thing. It's like, the more you work on projects like this, you'll start to develop an intuition for how the model architecture should be shaped. Like, if you need a more complex model, you would have like 3 or 4 of these stacks before you get into something like a pooling. However, the image data that we're working with is relatively simple. So I just had 2, and honestly, you could even have 1 if you wanted to, and we could just comment this out. And you just start to develop like a feel for it and understand what works better depending on your input data. But like there is no typical format for it, if that makes sense. It just doesn't exist. There's no typical format for data.
Okay. And then
It's just that a convolutional neural network is made up of these components, and how you organize these components is something that comes up to judgment and expertise in developing some models like these.
okay, and then so what that first convolutional layer,
Mm-hmm.
how come there's so much within this layer and you don't ever repeat, like what makes that first layer?
Oh
is it
yeah,
like-
because the following layers, they infer it once you specify it in the first layer. Like the input shape, right? The input shape of the first layer has to be the dimensions of the image, right? 32 by 32, which is what this is just grabbing 32 by 32 from the X-train array. However, the later layers, they're not going to be 32 by 32, right? It gets smaller and smaller. So as a result, it's inferring the input shape. So it is taking in an input shape, but we just don't need to specify it. It automatically picks it up for us.
Thank you.
Yeah, it just makes life easier. Like you could specify the input shape if you wanted to, but you don't have to because it'll do it for you. That way you don't have to do the math. Remember how we had to do the math where a 3 by 3 fitting into a 7 by 7 turns into a 5 by 5 output, right? Why should we do the math when we could just let the model do the math for us? It'll automatically pick up the input shape from the previous step.
And wait, so that padding, same, how come you repeated that?
That's because I needed to zero pad the border again. I actually think I was running into some bug in my input dimension, so that's why I added this in. I coded this like 2 or 3 months ago. It's been a really long time. I don't remember.
Okay.
Yeah.
And so that padding saying it creates the zero border, how big is it? Just an infinitely sized zero border?
Well, it basically morphs. It morphs to the size of how well the kernel fits into the image.
Oh, so it takes into the account the kernel, like how that'll work with the image, and then it'll okay. So
Yeah,
it all
I'm
interacts.
yeah, they all work together. That's why they're all parameters in the same conv2d function.
That's really cool.
Yeah.
Okay, thank
All
you.
right. Sick. Let's move on. Let's compile this. Did we already compile this? We can do it again. Doesn't matter. And now let's move on to the next thing. Let's take a look at what our model looks like with model.summary. And if you print out model.summary, now you should see a really nice printout of what our model looks like. And Shreyas, this should answer your question here. Look at this second convolutional 2D layer. Remember, we never specified the image shape, but look, it already picked it up that this is going to be a 30 by 30 input.
Yeah, wait, mine just gave me an error and it said invalid syntax and it's pointing to the word model. But not the first model, just one of the models, like later.
You might have forgotten a parentheses somewhere along the line. Send a screenshot or something in the chat. I guess that was a good time to run a reaction if you got your summary to print out. Were you able to print a model summary?
You don't active. It should be activation equals relu, right?
Oh yeah, you forgot the equal signs. Wait. Activate.
You don't have them.
No.
Oh wait, no, you don't need it.
That would be if you were passing it inside of the function. Where have you gone? Did you try running it again? Just try running it again.
No, same problem. Invalid syntax, arrow pointing to model, end of model.
Go ahead and I guess just copy and paste my code that I put in the chat and just paste that into a new cell below it and run that so that you don't lose all of the notes that you took.
So I'm just gonna put everything I did into a comment and just moving on. Yeah.
Okay, yeah, that
Copy
works.
and paste what you did into a new cell. Reaction.
You misspelled kernel size. Yeah, I think that might be the issue. Wait, but I mean, it's affecting it later, but you spelled kernel with an A up here. I don't know if that will change anything, but.
I can give it a try.
Yeah, go for it.
Nope, still gave that same problem.
All right, yeah, just go ahead and copy paste it. I think you just have a missing parentheses or something somewhere that I can't see. Yes, you do have a missing parentheses on this. That's why it's giving you a invalid syntax. There should be 3 closing parentheses on this line over here.
Oh.
Yeah, so basically it thought that you were trying to pass in model.add activation inside of the previous line because that parentheses never closed.
Okay.
Yeah, if you add that in, you should be good.
Okay, so now I did, and now it's saying model.compile. Can you show me your compile line?
Yeah.
Can you like? I can't see the. Okay. Saying positional argument follows keyword argument. Here, model up. I probably just forgot a comma somewhere. Oh, I see what I did. I think, never mind.
Got it?
No.
Is it not
Oh,
working?
I see it. Metrics. I did not put equals.
Oh, okay.
Oh, wow. Now it's giving me another error. Init missing one required positional argument filters.
Yes. You put
Why?
filter instead of filters. Up here at the very
Oh.
Me.
the
Oh, would
S.
you look at that? It worked.
Great.
Later. So the model dot summary, right?
Yeah, model.summary, open close parentheses.
It worked.
All right, cool. All right, awesome. And then your final layer as a sanity check, you should always check your final layer. The other stuff in the middle is pretty irrelevant. The model will do its thing, but it should be 10 units long. All right, let's train our model. And now what we're going to do is actually, you remember how I was talking about in the slides, how we can stop our model when it starts to overfit automatically? Well, what we can do is implement this, and it's called early stopping. Pretty self-explanatory name. From TensorFlow.keras.callbacks, import early stopping. And then we're going to create an early stop variable. Early stop equals, or I guess an object stopping. And what we want to do is we want to monitor the validation loss, right? The minute the validation loss starts to spike and starts to overfit, we want to just shut down the model, right? We want to shut down the model so that it doesn't overfit. So we want it to monitor our validation loss. And then another really nice feature is that you can pass in what's known as a patience. So what a patience means is that even though when it detects overfitting, it'll go another whatever, like let's say we pass in 3, it'll go another 3 epochs, like it'll still keep trying for another 3 epochs after it detects overfitting, just to make sure that it doesn't fix itself after a couple epochs, if that makes sense.
Wait, no, could you explain that again?
Yeah, so it's like how patient the model is after it detects overfitting. So let's say we're 10 epochs in and it starts detecting overfitting, right? But it's not going to shut it down right away. It's going to go all the way until epoch 13. And if the model is still overfitting, then it's going to shut down. But it won't shut down right away because maybe the model will fix itself and not overfit any longer, if that makes sense. So it's going to have a patience of 3 epochs before it actually shuts down. And if it's overfitting for 3 epochs straight, then that's where this early stopping will kick in. All right. Now let's create a variable called history so that we can track our progress, but the rest of this is going to be the same as the last lesson. We're going to call model.fit. Remember, we need to pass in the X-train data, the Y-train data, and let's pass in a little bit of a smaller batch size this time. Let's do 32, but we're also going to do fewer epochs because this is image data. Let's do 20 epochs. We're going to pass in verbose equals 1. I think verbose equals 1, it like prints out all of that training. Maybe by default it's 1. I don't remember.
I got an error for the early stop. It said init got, oh, are you kidding? I put an extra S.
Yeah, I had the same thing, but I just spelled monitor wrong.
Yeah,
It's like it never stops.
Yeah.
Coding can be annoying in that way. The
My
worst
hand just
thing is
says
when it
drawn to
actually
pass.
doesn't give you an error and you don't find it and it just like keeps going on with its day. Like if you put in the wrong number, right, it'll still like do something, but it'll just do it wrong. And it's so frustrating to find stuff like that, you could imagine. And then we want to pass in our validation data, right? Because the model is going to use this for its backpropagation algorithm and just kind of like scolding the model when it makes an error or rewarding the model when it's good during this process. Make sure to put a comma after verbose. I just put an enter so that we wouldn't try to squeeze this all in one line. Once you call this, it should start training. Yay. Oh no, wait. Okay, you see how this is taking forever? It says like 3 minutes and 45 seconds, right? We don't have that kind of time. We can't wait 20 epochs for this to train. So when you're thinking about video games and video game PCs, you usually want to have like a good GPU, right? If you want to perform a lot of graphics
Wait, should
processing.
we stop the execution?
Yeah, you can stop the execution or you can just leave it. We're going to stop it anyways. But when you're thinking about graphics, actually what's very strange is that the same graphics processors that are very, very good at playing video games or rendering graphics for 3D printing or for video games or for so on and so forth, these same GPUs are insane at quickly processing image data. And it just happened to be that they were optimized for a process like this, right? And it's a similar thing that's going on, except we're performing a convolutional operation on image data. So what I'm going to show you is a hack that basically takes this training time from around 4 minutes to just 12 seconds, simply by changing the settings of our notebook. And this is called GPU optimization. GPU optimization, Google Colab provides it to you for free, which is just mind-blowing that such a great service is offered for absolutely no money. So what we're going to do, go to runtime and go to, I guess, interrupt execution if you haven't already. And then what we're going to do is go to runtime, change runtime type, and we're going to pick this hardware accelerator. So what a hardware accelerator is that it's some sort of physical component inside of Google servers or whatever that are optimized for performing some sort of operations. You could have a TPU, which, is that a tensor processing unit? I'm not sure, but a TPU is very quick at doing math. A GPU is very good at dealing with image data. So change this to GPU. And once you've changed it to GPU, press save, and then just rerun everything from the top because you're going to lose all your variables. So just rerun everything from the top. Just go to the top and just spam shift enter until you get to the bottom. And you'll see it's like witchcraft, and it just like speeds it up insanely. It's really, really impressive.
Wait, can you put what patience is again? I'm gonna write a comment.
Yeah, sure. So what patience is that when the model starts to detect overfitting, we don't want to shut it down right away. We want to give it some like buffer, like some margin. So patience is just, it's the number of epochs that it's going to wait before shutting down the model. So once it detects overfitting, it's going to wait 3 more epochs before actually shutting it down, just in case the model corrects itself, or to make sure that the model isn't actually overfitting and it was just like a little bit of an anomaly during the training, if that makes sense. It has a patience of 3 epochs before it actually shuts down the model. And if you take a look, you should have like sub 20-second times now, and that's just an insane achievement. We didn't change anything in the code. We simply optimized our notebook for handling image data by applying a GPU optimization hardware acceleration simply by changing the runtime settings of this thing. So if you guys are working on image data projects, man, is this nice to have. And it's actually one of the reasons that I built a PC at home, was to have this GPU acceleration. Otherwise, my project that took 30 hours to train would take a lot longer than 30 hours to train, and that's just really sad.
Wait, so oh, okay, that makes sense. It would be like super fast if you had like a dedicated GPU in your PC, and then you optimize your GPU.
Yeah, exactly. Because by default, if you were to run this on your local computer, right now we're running it on Google servers. It's just like a Google Doc, which isn't actually saved to your computer. It's saved to your G Drive account. But if you were to run this locally, it would actually go to it would be all trying to do all these operations on your CPU unless you had a dedicated GPU in your laptop, right? GPU, for those who are unfamiliar, graphics processing unit or graphical processing unit.
An error.
An error?
It says, please provide data which shares the same first dimension.
Which shares the first dimension. You might have written this command, the input shape command, wrong. Let's take a look. check if this looks exactly like what you have on your input shape. And I hope everyone else is training right now.
Yeah, mine looks exactly the same.
Go ahead and send a screenshot of this entire cell then.
What, the one with where we added the layers?
Yeah. And I just sent a poll to see if your model is training. So let me know in the chat. Yeah, Palash said it's a hack. If you were referring to the GPU optimization, yeah, it is. People that don't do it, man, they're just like missing out and just wasting time. Look at these sub 20 speeds. I'm not waiting 4 minutes for every epoch. No, no, no. Does look good to me. Let me check with mine. Can you send a pic of your error as well while you're at it?
Yeah.
Oops. I've never seen that error before in my whole life. What the heck? Let me look up the error. I've encountered many an errors, but I've never seen that before. Data cardinality is ambiguous. Can you share your notebook with me on Google? It's saying you might have matched Xtrain with Y test by accident on some of them. On somewhere in your notebook. I think you accidentally put Y test where there should be a Y train somewhere.
Yeah, I sent it. It's called cnn.ipynb.
All right. There we go. If you read that error, right, that's probably exactly what it is. It says X sizes is 50,000 while Y sizes is 10,000, right? So you probably matched the testing data with the thing by accident. And for everyone else, hit that thumbs up on the reactions if you're training, or let me know if it's not working. Let's debug this really quick for free. That's good. That's good. Yes, there we go. Yeah, so in this, take a look at this cell over here. You accidentally did X test equals X train divided by 255.
X test equals what? Oh,
Yeah, you just put the test data set by accident because we just want to normalize not the train data set again. Yeah.
do I have to run everything if I change that?
Yeah, just run everything again. Have you changed your GPU settings?
Yeah.
Okay,
I'll
yeah,
just
so
run
just
all.
run it from the top. All right, got that figured out. Let me check the Discord chat for the thumbs up.
So, do you know exactly how the loss and accuracy is calculated?
Accuracy is very simple. Accuracy is just the number it got correct out of the total number, right? Just like on a test, like you can calculate your grade on the test, right, by the number you got right divided by the number of questions on the test, right? So it's the same metric. Loss is very complicated.
Okay.
I know how it's calculated, but it involves a lot of calculus or a lot of functions that are linked together that is, I guess, out of the scope on what we're exploring. But yeah, You can just think of it like a way to measure error, and I think that's pretty decent enough, especially if you haven't taken a higher level math class yet. And Sri, let me know when you get your model trained so that we're all on the same page. And we
Yeah,
can
it's on Epoch 5.
All right, cool. Yeah, so I guess we'll just while Shri's code runs, hopefully yours is done. Hopefully everyone else is done by now. Now we can move on to plotting these losses and seeing whether or not we overfitted or overfit. Is that the term for it? We're going to import matplotlib.pyplot as PLT. Let's go ahead and do losses equals history loss.
Wait, will it let me write code while
Yeah, you
my
just press this.
thing is
You just have to
training?
press this plus code button manually, and then it'll do it
Wait, where do I press it?
right here.
Oh, okay.
Did it create a new cell?
I think, but I don't think it's under my training.
Oh, so click inside of your training cell and then press the plus code button so that it creates one right
Oh,
after.
okay. There we go. It works.
Nice. All right, we're gonna create our regular loss and also our validation loss. And then we're going to create a nice matplotlib plot with all these on here. And we'll do the same thing for validation. I'm not 100% sure if this could work. This is off the dome. I did not have this code pre-written, but we should be fine. Let's title this training and validation loss. And then I guess you guys let me know, what is our X label?
X label would be X train.
Not quite.
Wait, no, the Y train.
Not the Y train either. When we're plotting a loss curve, like the J curve, what's on the x-axis? It doesn't have anything to do with the data.
The epochs? Or
Yeah,
trial?
the epochs, right, or aka the training time epochs. Because as we go further and further into epochs, we want to have lower and lower loss, right? And then, so what's our Y label then?
The loss.
The loss.
Yeah, loss. Perfect. And then we can call plt.legend so that it'll automatically create it for us. And then last but not least, call plt.show. There we go. We have a very, very decently performing neural network on the CFAR10 dataset. Pretty impressive. You can see where we started overfitting around, it got pretty severe around 14, right, where they started diverging from each other. And it looks like our early stopping kicked in around 18, right? So patience of 3. So before then, right, it's not the exact moment that the model starts overfitting because like it's not overfitting until it passes a certain threshold, right? Maybe they're not going to be perfectly on top of each other. The MNIST model or the house model that we created was just very, very perfect in terms of having them overlap. But yeah, this is a very, very strong performance of a model, and we were able to use early stopping to just cut it off. And you notice how we train for like more of the epochs, right? But we wanted to stop the model earlier in case it went on. So let's say we train this for like 100 epochs. There would be no way. Oh wait, we never even put early stopping into here, did we? No, we forgot to put early stopping inside of this. Is it callbacks? Yeah, it's callbacks equals early stop, I think. Yeah, I forgot that line of code. Sorry, guys. Just add this in, and you can run it later, and it should probably stop it before 20 epochs. Yeah, because it looks like it's overfitting before it hits 20. But yeah, again, that's callbacks equals early stop. You put that inside of here. I was wondering why it went all the way to 20 epochs.
Wait, so with early stopping, what did I just do? Oh, I just can't spell the word early. So with early stopping, so that epochs that we give 20 epochs, but early stopping, depending on if it's overfitting, it just won't let you complete the 20 epochs. If it begins overfitting, it'll just cut it
Yeah,
off.
it'll just stop before then, and that saves a lot of training time as well, right? Especially for like a large scale project that you're doing for science fair that might take hours to train because the images aren't just teeny tiny 32 by 32, right?
Yeah.
You would want to use early stop so that your computer isn't just unnecessarily running and just overfitting all the time, because you're not going to be sitting there like for hours just staring at your loss, right? So you want to
Yeah.
put early stopping in so that it stops by itself. It's really, really nice and useful.
Could you go back down to the graphing of it?
Yeah, sure. All right. If we want to get to the malaria example, I really want to do it because I think it's a fun project, but we will go like very, very over time. It
I
is
should
it
be
is
able
up.
to stay.
You should be able to stay. All right. Yeah, I apologize. If you're not, I will just send you the code and the recording. But yeah.
I
Wait,
got
did-
an error for the callbacks.
You got an error for the callbacks. Did you make sure you put it inside of brackets, like an array?
Yeah.
What?
Did you put
Oh,
callbacks
man.
equals?
Yep. I sent it.
Oh, you sent it. Let me take a look.
Wait, this is really weird. So okay, so I think the callbacks worked because it might have, because my epochs stopped at epoch 6.
Yeah.
But then when I look at my graph, it's like the blue and orange line are like super far away from each other.
You might just want to run it from the top in case you accidentally
No,
ran
I
something.
accidentally put it in the X test, Y test.
Oh, I see that. Yeah, it's still in the parentheses. Yeah.
Yeah.
Okay, great. Hopefully it's working now. And look like, so mine stopped around 9, so yours should stop anywhere between like 8 to 10. Yeah, so this is a correct graph. They're only like 0.1 away from each other. That's why it looks so strange, Shri.
Oh, I reran it because
Yeah, it's like yeah, you don't need to rerun it. This is actually a good graph. Man, this is getting confusing to explain. This is a good graph. It's just 0.1, 0.15 away from each other.
Mine is still going and it's on epoch 12.
Okay. Yeah, maybe it'll just kick in a couple epochs. But yeah, this graph is fine. It's just out of proportion because of the x-axis, right? So it just magnified this really small error. If we want to, we can just remove early stopping for now, just so that I can show you what the plots are going to be looking like. But in the meantime, let's copy our code for the loss graphs and let's make a graph of accuracy. This is going to be the first time we're graphing accuracy.
Wait, can you go back to callbacks? Like that, like to show the thing, like what it's supposed to look like?
Oh, I just took it out, but you basically inside of here, you pass in callbacks equals early stop as such.
Yeah, mine finally stopped at 15 epochs.
All right, cool. Yeah, plot that and see what it looks like. I'm going to remove it so that the graph looks a little bit more similar to what we did in the slides. But if you understand what that was showing, right, it looked so far apart on my screen, but it was just 0.1 apart. In the grand scheme of things, it was pretty spot on. All right, but yeah, we're going to paste in the code for losses and let's make some accuracy graphs now.
Whoa, mine is a very interesting graph.
Yeah, paste it in the chat. Let's see what it looks like.
Oh, I reran mine and it's still going until it's on epoch 10.
With the early stopping or without?
With
Yeah, it like changes every single time. Remember, a neural network has random weights and biases, so it's not going to be the same every single time. Yeah, so that's actually like Shreyas, it looks strange, but it's actually not that bad. Like they're only like they're only 0.6 apart. If you look at the or the y-axis, look at the y-axis.
Yeah.
They're only 0.6 apart, so it's actually a very small difference.
Yeah, I
It's just
saw
that
that.
this thing is weird. You can actually fix it by creating your own custom like scale on the x-axis, and then it'll look a little bit better. I just removed it and I'm rerunning it for the sake of demonstration, since I seem to have confused some people as to why the graph looks so strange. But yeah, let's plot some accuracies. You can rerun it without early stopping if you want to.
But at what time is this gonna end if we end up doing the malaria one?
It's like equally as long as this example, so like 45 minutes to an hour, unfortunately. I don't know. I guess I could do it like tomorrow. I don't know. I don't want to like stretch it out on a day I said I wouldn't be teaching on. But yeah,
I would prefer we do it. Can we do it tomorrow?
I can do it tomorrow if everyone else can do it tomorrow. Otherwise, I can just do it today, and then I guess you can watch it
tomorrow or today.
tomorrow or today.
Same.
Same. All right. What about you, Arush? And then maybe that might work for Noah.
Yeah, because Nora.
Yeah, we would start at
Noah's
10 and we would finish at 11, so it's not going to be like, yeah.
Oh,
What about you,
Okay.
Arush?
Oh, this is actually much better. So mine stopped at epoch 16 and my graph is actually like interconnected somewhat.
Okay, cool.
Wait, so you're rerunning your data without the callbacks. Is it fine if I use mine with the callback data?
Yeah, you can use it with the callbacks. It's better practice to do it with the callbacks.
Okay. I was curious because like you said you're gonna do it without it. I was like, does that mean I shouldn't be creating graphs with callback data or with a model that's
Yeah, I just didn't want the graph to look weird, just because I wanted to analyze it with you guys. So I'm still waiting for it to train. Any minute now. Luckily, we are GPU optimizing and it's very fast. Imagine teaching a computer vision class where like the model takes like hours to do, right? You would have to wait until like the next day in order to see what happened. All right, but yeah, in the meantime, let's go ahead and code in our accuracy plots. My computer is lagging. Come on. We went too back down. So just copy your graph.
Wait, I copied and pasted my graph, but
Well, make sure to like change the history.history. We have to change everything that was accuracy into loss.
wait, PLTX label should be. Wait, is the Y label accuracy?
The Y label is accuracy, correct. I'm still getting very strange. The heck?
Accuracy. What should the title should be like?
Yeah, I don't know what's going on. This is okay. So I'm just
my graph seems the exact same.
Yeah, it looks. Does your graph look like this?
No, but it looks like the exact same as my first graph with the loss on epochs.
1 second. Let me see. Okay, yeah, I'm getting really strange. I'll fix this and let you guys know tomorrow, but this is my master code file. I'm simply copying from it. And this is what my loss looks like, right? This looks like something we're familiar with. And then my accuracy looks something like this, which is also something that makes sense, right? As you increase epochs, you increase accuracy, and looks like our model was just around 80% accurate at the end of the epoch training. That's really strange. I'm just going to try, I won't hold you guys up, but I'm just going to try rerunning it, or maybe I missed something in the code. I'll debug it myself. I don't want to hold you guys while I'm doing that. But what we will do is quickly write some of the code for what we can look at, which is called a confusion matrix. And that way, once I fix this very strange bug, we can run it tomorrow and analyze it together. So for the meantime, just copy this down, and then we'll talk about it tomorrow.
So I got a different graph.
Did you get one that looks more reasonable?
I don't know about that. Here, I'll just screenshot it real quick.
I've taught the CFAR 10 dataset like 6 times, and I've never seen a graph that looks like this. What the heck is this? That's better than my graph, that's for sure. If everyone else wants to send their graphs in the chat, we can look at if anyone's is making sense. I think I might have missed something. That's why it looks so strange. Actually, Shreyas, yours doesn't look that bad, to be honest. But it does look very erratic, though. All right, let's just copy this code down. I don't want to keep you guys longer.
Wait, what is confusion matrix?
Shri has the perfect graph. Not for accuracies, though. Why is the accuracies returning the same thing as the loss? Okay, I'm going to fix this later. Let's copy this down, and I'll fix it later. Shri, your loss curve looks perfect, though. Your accuracy looks very strange. Your accuracy just looks exactly like your loss. It's like you grabbed the same things from the dictionary. Did I just do it wrong? Let me try something really quick. History.
Wait, Shri, I can see why you got the same graph for both of them. PLT, when you did PLT.plot val losses and losses again. You didn't change them to accuracies and val accuracies.
Yeah, here's what I imported, Arush. Or did you mean at the very top? Wait, what did you say, Shreyas?
On Shri's, I think the reason why he got the same graph is because like he didn't change the losses and value losses in when he was plotting them.
That's just the title. That shouldn't matter. If that makes sense.
But it says losses and then comma label equal like. Shouldn't that be accuracies?
Oh yeah, you're right. Yeah, oh yeah, the variable, he passed in the variable. Yeah, you're right. All right, let's quickly do this. And what I'll do in order to explain it, I'll show you my master file, which has it correct. So what we're going to do is we're going to round the labels, which means we're going to reverse one-hot encode them. Like we're going to turn them from zeros and ones back into the proper labels with the argmax function. If you remember the argmax function, it returns the index of the maximum value in an array, right? So if we have a 1 at location 6, it's going to return a 6 because it's the index of the maximum location where everything else would be a 0. So we're going to do this, specify axis equals 1 so that we get the proper orientation. Then what we're going to do is do predictions equals model dot predict classes And we're going to do that on our X test data, right? Our completely unlabeled or unbiased predictions on this. And then we can print out a nice thing called classification report. And we want to pass in the rounded labels as well as the predictions here. So what a classification report is it's a summary of all of the statistics from our model. It includes things like precision, recall, F1 score, and accuracy. So what these metrics, these are other ways to measure accuracy. Remember how I talked about that accuracy is not the best metric when we have unbalanced classes, right? So we would want to look at things such as precision, recall, and F1 score. They're not very difficult to understand. There's a Wikipedia page on them to read it. I did want to go over it, but I think we won't have time. But yeah, you can look up what precision, recall, and F1 score are. Ideally, in a perfect world, all of these values are 1.0. So basically, in a perfect world, you want to optimize your neural network to achieve as best results as it can, so closest to 1.0, which would mean like 100%. I spelled that wrong. Predictions. There we go. All right. So it looks like it was pretty good at, it was really good at class 1, right? It was almost 90% across the board on precision, recall, and F1 score. So it looks like the model is very good at some of these classes, right? This actually didn't perform bad at all, even though the graph looks really strange. But yeah, it did pretty well. So if we wanted to take a look at what our predictions are looking like, it's like this, right? This looks exactly like our labels or our Y labels from the very beginning, where we have 3, 8, 8, so on and so forth. These are simply our predictions as generated by the model. And we can compare them with Y test, and they should be similar or it should be the same in the cases that it got it correct, I guess, if that makes sense. Oh, these are one hot encoded. Let's just look at the first 3. So here we have it, right? These are the predictions generated by the model. The first prediction was a 3. If you take a look at Y test, look where that 1 is. It's on index 3. So that was a correct prediction. And then if you look at the other 2 predictions, there's an 8, there's an 8 again. So it looks like the model actually got these first 3 images correctly analyzed inside of the data set itself. Yeah, Shri, yours looks perfect. I don't know where I went wrong. It looks like you have a perfect code. Yeah. Why is mine looking so strange? And Palash, yours also looks quite reasonable. It's just overfitting. And it's overfitting around 80% accuracy, which is fine, right? Because your validation accuracy was around 80%, which is still pretty decent. And that's just about what we can see over here. So Palash, yours looks fine as well.
In plt.plot, you have to change accuracies and val accuracies.
Did I not do that?
Like, I think you have losses. You need to change it to accuracies and val accuracies instead.
Yeah, but my losses graph is still like looking very strange.
And then you can just change like the label and stuff.
Yeah, I guess this is not bad at all. I can just range it from 0 to 1. Yeah, this looks actually exactly like what Palash's code kind of looks like. Palash has an error. Did you create predictions with model.predict classes on Xtest?
Yeah, I forgot to do that.
You're good. Yeah, we just got to generate some model predictions really quick so that we can compare it with the actual predictions. All right, and then for the sake of time, I'm gonna just paste the next 2 things in the discussion chat. And I'm gonna explain what a confusion matrix is really quick because I think that's probably my favorite metric when I'm doing deep learning projects. So go ahead and copy all of these in.
Copy what?
I sent it in deep learning discussion. Go ahead and there's 3 separate lines of code.
Should we put these in different cells or in the same one?
Yeah, in different cells.
Okay.
I should have put some sort of division between them. My bad.
Should we run each of them before we add the new one?
Yeah. Your first one should look like this. Your second one should have a bunch of decimals in it. And your third one. So even though the model looks strange, it actually did really, really well. Actually, I don't think I had anything wrong with my model. It's just the graph axis was just strange.
What is this third? What does the third one do?
Yeah, so the third one is actually just a heat map of the first one. So what this is, it's called a confusion matrix. So what a confusion matrix is, I hope you guys got this over here. Ideally, in a perfect world, everything along this diagonal in the middle, it should be a 1. And a 1 meaning 100% of predictions correct. So let me actually do one more let me introduce this concept a little bit better. CF matrix, is that what it is? CF matrix, okay. Okay, I'm gonna paste one more thing in the chat. Oh, that's why I did it. Never mind. Yeah, so let's just look at this little, let's look at one cell at a time. So what a confusion matrix does is that it plots all of the model's predictions against all of the correct predictions. So if we were to look at this over here, right, this blue looking graph over here, that means that on this side of here is the model's predictions, and on the y-axis is the true predictions, or maybe it's the other way around. It doesn't matter too much, but what it's saying over here is that this cell, this is where 0 matches 0. So let's say the 0th cell was the airplane. So that means 83% of the time, the model correctly guessed that it was an airplane when the computer or when the person that annotated this data set also said that it was a computer, if that makes sense. So if we were to look at something like number 3 over here, so we go to 3 by 3. So that means 61% of the time, the model correctly identified that it was class 3 when in actuality it was class 3. So that's what the diagonals means. What do these numbers that are not in the diagonal mean? Does that make sense? Does the diagonal make sense, or is that confusing?
So
What
could
exactly
you
is a confusion?
Oh wait, Trace can talk.
Oh, sorry, thank you. What exactly is a confusion matrix again?
Yeah, it's like determining how many times the model was correct in its predictions. Let's take a look at a Google image. All right, here we go. Oh, nice. We have the iris data set. We have a confusion matrix on the iris data set. So here we go. Any second now. There we go. This is a confusion matrix without normalization. I'll explain what that means in a second. So on the y-axis over here, we have the true labels. So that means, remember, we already have an answer key to this problem. So the true labels are on the y-axis, and the predicted labels are on the x-axis. So out of our data set, out of the 13 Setosa images, the model correctly predicted that it was also Setosa, right? Because this Setosa matches up with this Setosa. Does that make sense?
Yeah.
So the same thing with versicolor. So that means there were 16 versicolor images, right? 10 plus 6, right? There were 16 versicolor images, and the model correctly guessed it 10 out of the 16 times, and it mistook it for Virginica 6 times. Take a close look at what this is plotting. So 10 out of 16 times it made a correct prediction, right? Because that's where the versicolor, as annotated by the by the person who created the data set matches up with what was created by the deep learning model, right? However, 6 times it was incorrect, right? And the reason that it was incorrect is because this is versicolor matched with virginica. So that means the prediction was virginica, but in actuality, it was versicolor. So the 6 over here represents incorrect predictions. Does that make sense?
But so everything that's not within that first diagonal,
Yeah,
that main diagonal that goes through each one, that's
Yep.
really just each one 0 intersecting with 0, 1 intersecting with 1.
yep,
One of those, everything that wasn't in there was an incorrect guess. or
exactly,
prediction
exactly.
Model.
Yeah, exactly. And that's why we plotted a heat map, because ideally we want the darkest squares to be along the diagonal. And it looks like that was true, right?
Yeah.
And this is really useful for us because we can look at some of the darker squares that were outside of it. So looks like 5 was commonly mistaken for 3, right? 15% of these predictions for 5 were mistaken as 3, and then we could maybe see maybe that was the difference between a car and a truck, right? Those are similar things, so the model got more confused on those predictions, if that makes sense. 15% of those were incorrect, but the vast majority, right, 66% were still correct. So yes, everything that's not on this diagonal is an incorrect prediction.
But so going back to you were saying with about versicolor and like that, can you scroll down like that virginica, that's 6?
Yeah,
So in reality, so that always the y-axis is the true label, and then the x-axis is the guess, and then the diagonal is just every time the true label and the guess line up and match.
yeah, exactly.
In this case, yeah, what you said. Okay, now I get it. So 6 is it was a versicolor, but was guessed virginica.
Yeah, but the model said it was virginica, even though it was a versicolor. Yes, you're exactly right.
Yeah.
Yeah, it's not very hard to understand this, but yeah, is anyone still
Took me a
confused?
second to
Yeah.
kind of grasp that. Yeah, thank
Yeah.
you.
Okay, I have one question. So where's like, so on class 0 and column 1, would that mean
Yes.
that the model predicted that 1.5% of the time it was in column 1? Like I know that's hard to understand, but I don't know how to put it in the right word.
I'm not sure what you're saying because your numbers might be a little bit different than mine. This is what's called the normalized confusion matrix. So this is just the percentage. So this was the raw data, and this is a normalized. Our raw data is right here. So 827 times the model correctly guessed that it was class 0 when in actuality it was class 0, and all these other numbers outside of the diagonal are incorrect predictions. Normalized confusion matrix is just the percentages. So 83% of the time, it correctly identified that this was class 0 when in actuality it was class 0. So your question, if there was like a 0.15 anywhere that was not on the diagonal, then yes, 15% of that class was misidentified by the model.